Hello and welcome back. We'll start this section by introducing word-to-vec embedding and how you can use GenSim to train a word-to-vec model and a list of sentences. As we described in the slides, the word-to-vec algorithms are skipgram and CBOW, or continuous bag of words. In the following, we show how we train a model for either of them. It is worth mentioning here that there are two ways we use word-to-vec vectorization. We can train the model on our corpus or use the pre-trained models, which means models which are already trained on large corpus of text data. In this tutorial, we learn how to use GenSim to train the model on our custom corpus, in addition to how to use pre-trained models. And finally, how to train bag of words or BOW and TF-IDF models. Please note that if you want to use bag of words and TF-IDF, you need to train your own models. These models are based on the definition and need to be trained. We want to ignore warnings, so we import warnings and then we set at the filter warnings to ignore all of that. We import the libraries as we need sentence tokenize and word tokenize from NLTK and also GenSim, and then we import word2vec from that. To train our word2vec model, we need text data. We put an example here as 2 sentences. The input of our model needs to be a list of tokens. First, we tokenize the text by sentences, and for each sentence, then we tokenize it into words. Let's see what the results look like. So these 2 sentences now is the list of tokens. We want to review how the model's word2vec works. This contains all word2vec families of algorithms. But GenSim has a class of word2vec algorithm, and you can set different parameters. You see here we have like different parameters that we can set. But in this tutorial, or in our case, we want only work with a limited number of them. The main one is the sentence, is a list of tokens. This is the way that we provide our text data. Vector size, which is also optional, is the dimension is about the dimension that we want and we are looking for to have for our word vectors. We have window, which is the maximum distance between the current and predicted word with the sentence. For example, if you set it as 2, consider only two words after and 2 words before of the current word. We explained this in the slides, that how it works. Minimum count is ignore all the words with total frequency lower than this value. For example, if you set it as 1, so or set it at 2, any words which has a total frequency less than 2 doesn't consider in the in our model. SG, which is very important here, that by default is a value that by default is CBOW, but if you set it as 1, this means that you want to train your model by a skipgram. So we import our data, so which has a list of tokens, so it's the query format that we want. So minimum count is 1 because in our case we don't have that much sentences, and the size is 10 because we want to vector which has a dimensionality as 10. Windows 3, we consider 3 words before and after. There's a possibility when you train your model here that we create the model, but it's possible that we want to save it. For example, if it takes a lot of time to create and train your model on a large corpus, so you want to save it, and anytime you want, you can load it again using word2vec.load. You can find a name, and then after that, you can again load it. There's a possibility that after you're creating your model, so the model here that we name it as model 1, and then we want to see the vector of one word. For example, house. House is one word of this, and we want to see is here. So we want to see what is the vectorization. And to access that, so we use name of the model .wv, and then we name the word that we want. And here you see is array is a vector which has 10 components because we set it as 10 here. It's also possible that get access to the most similar words from one word. And here that we set, for example, on, and then we want to see what are the similar words based on that. You see here that father is the most similar word to that, and this is the similarity score. This similarity score is based on cosine similarity. We can also put top as top 10 or 5 or 2. It depends on how many similar words we want to show. For the cosine similarity, we can only, so it's only the score or the cosine similarity score that we show. So it's a model dot similarity, but we need to give 2 words. And then when we put 2 words, it shows us, for example, mother and father, we have the score that is negative. And also, for example, car and father, we have it as also negative similarity. So it means that it's not similar. And then again, here, that we want to create a model using a skip gram because we set here as SG equal to 1. And then we put the windows at 4 here now, and then we do the same thing. You can see the vector of that word, and then after that most similar words, and then the cosine similarity. Let's see here that how you can use pre-trained models. GenSim has a good library, and has a good class here that we have, or a function that is downloader. So gensim.downloader.info, we can get access to the information, which is because we want to have the list of existing pre-trained model in GenSim. So for that one, we only want to get the info of that, and we want to have the name of the models. You see here that using FastText, ConceptNet, Word2Vec, Glove, and also all Glove. And then when you have the list, you know that what are the lists available, and then after that you can load these model. For example, here is the Glove Twitter that we want to load it and put it as Glove vectors. So it's already trained on a large size of corpus, and then so it's available. So this is kind of pre-trained models that you can read. And then you can find the similar words. If you choose, for example, Twitter, you can see the most similar words of the word Twitter based on the vectorization of Glove, which happens and trained on Twitter text data. The last part is about sentence embedding with TF-IDF in bag of words. for this one is we use df-idf vectorizer, which is for vectorizing of based on TF-IDF, and counter vectorizer is a vectorizing based on bag of words, and we take it from the modules scikit-learn or sklearn. We also import pandas because we want to show and print the data as a data frame. The input of counter vectorizer and TF vectorizer, when we want to feed it, is the format should be a set of document or set of sentences. So the data we had was sentences, and then after that we tokenize it. So we have list of sentences. We instantiate the vectorizer object, and then after that convert the document into a matrix using that data. We retrieve the trends found in the corpus. So now is count tokens, and TF-IDF tokens are our vectors based on TF-IDF here and bag of words. So we create a data frame, and then after that, the columns is the these vectors. So let's see what is the value. You can see here that the doc1, which is the first sentence, doc2 is the second sentence. And you see here when the word exists in the first sentence, so this is the first vector for sentence 1. If the word, this is the frequency of that word in a sentence. So 0 means that there's no word in the first sentence. The size of this vector is the number of unique words in whole document. And this is true for TF-IDF vectorizer. You see here that the size is the same as it's the size of the the size is the number of unique words in that sentence. In the slides, when we want to compute the TF-IDF for 2 sentences, we use exactly the same example, so you can compare. But if you compare, you can see that we have different TF-IDF value for each word in a sentence. And this is the difference. As you can see, the value of TF vectorizer from sklearn is different from what we manually computed in the slide. Based on scikit-learn website, TF-IDF of a term T in a document D is computed as TF-IDF is equal to TF multiplied by IDF. The value of TF-IDF is the same as we define, is the term frequency, which is the frequency of a term T in the document D. However, they added 1 to the value of IDF because they want to not ignore the words that appear in all documents. And that's the reason that you can see here that in the slides we have 0 by, because by is in both sentences, but here the value is not 0 because we add 1 to the formula. If the variable smooth IDF is true, so in skyline feature extraction the text here that we can set, you see here that the use IDF is true, norm is L2, and then when this value of the smooth IDF, here that we have it true, subliner is also true. So when is this smooth IDF here is true, then the formula for IDF will be like a different formula, you know, added here that we have a 1 plus n over 1 plus dft. But if a smooth IDF is false, the formula is n over 1 plus df. So this is a way that you can choose like different way of computation. So the final vector for document D is normalized based on the norm chosen here that you can choose as L2 or L1 norm. So it's better that you see more details if you want to know more about this and how they're different. But something that we can see here is, for example, the zero value means that this word doesn't exist. But in the previous case, when in the slides, when the words by, for example, was in the both sentences, we had zero. So there was no way for us to understand if the value is there or not. But now you can see that zero is only for the words that doesn't exist. For the assignment, take data we created in data collection tutorial and try to train the word and the sentence embedding models that you learn here, and then see that what you can get. Thank you.